Welcome back, everybody. We're busy revising some concepts about electromagnetism. Let's go and have a look what we're doing. So we recognize, to start with, that there are two types of processes that take place when we're dealing with electromagnetism. We can have electric current that produces a magnetic field, and we can deal with that in terms of electromagnets, where we recognize current passing through a straight conductor or a loop or a coil will produce some sort of magnetism. However, there's a second option, and it's my favorite one, which says let's rather start talking about doing something to a magnetic field, and let's see if we can do something to the magnetic field and a coil, if we can make some sort of electric current. And so this is called electromagnetic induction. And that's what we're going to focus on right now. So just to remind you that with electromagnetism, we said a moving charge creates magnetic flux. But when we're dealing with electromagnetism, a change in magnetic flux produces an induced EMF, or potential difference. Now, if that potential difference is across a coil that's part of a closed circuit, well, then we will have an induced current as well. So take note that if we've got a closed a circuit, then we'll have an induced current. These are related to each other, and they're related simply by Ohm's law, where we know that R is equal to V over I. So you can work out, for example, the resistance of the coil. If you know the induced current was a certain amount, and you know what the induced EMF was, you can work out the resistance of the coil, just linking it to another section. But we're not going to focus on that. Let's rather focus on the process of electromagnetic induction. And so I remind you that it's all about a moving magnet and its relationship to a coil. So if we move the magnet towards this coil, then we're going to see that there's a change in the magnetic flux that is passing through the coil. The coil has an area that is perpendicular to the direction in which the current is moving, and you can see that if the current is moving up, there's an area in the middle of the coil that is kind of at 90 degrees to that. And so we recognize that the magnetic field lines are also going to cut through this area that's in the middle of the coil. And so we've got to recognize that there's a change in magnetic flux. When the magnet is far away from the coil, there are not many field lines. As it comes closer, there will be more field lines. And so we can determine what's going to affect the induced current. There are a number of factors to look at. And so the first thing that we're going to say is, what are these factors? Well, the first factor we're going to look at is the number of turns in the coil. Whether it's got one loop or two loops or three loops or four loops, all those loops together create a bigger magnetic field when there's current passing through it, which opposes the moving magnet, and that's important. So the number of turns on the coil is very important. The second thing that's important is the strength of the magnetic field. Now, you can get different magnets of different strengths. Remember, we indicate the strength of a field by the closeness of the field lines. And you can measure them. We measure the magnetic field strength in Tesla. And so we're able to measure and rate different magnets, bar magnets, solenoids. We're able to rate them in terms of, this is a strong field, strong magnetic field, this is a weak magnetic field, depending on different materials used. We also are able to look at the change in the magnetic flux. And the change in magnetic flux is generally created by the movement, by the motion of the magnet. So if the magnet is stopped, there's no change in magnetic field. There's no change in magnetic flux. And so there would be no induced current. In fact, if the magnet was moving at constant speed, then it would still not induce a current, not induce an EMF. But if it's speeding up or slowing down or changing direction, well, then it's going to have a change in magnetic flux. And so when we move the magnet into the coil and out of the coil, that's when we get a change in magnetic flux. Those factors are really important. And these were discovered and summarized by a very famous physicist called Faraday. Faraday's law is probably one of the most important laws that comes out of the 1800s. And it has had a huge impact on devices that we use in our everyday life. In fact, without the idea of Faraday's law, there'd be a whole lot of technology that we wouldn't have access today. So let's have a look at what Faraday's law says. Faraday's law says the EMF induced in a coil is directly proportional to the rate of change of magnetic flux. And here we have the equation. So I'm going to break it apart just for the moment. And I'm going to say, it's telling me that the induced EMF is directly proportional to the change in magnetic flux. The phi bit that represents the field strength times the area that is perpendicular, and that cos theta does the little correction if it's not at a normal area. But it doesn't just say it's directly proportional to the rate, it doesn't say it's proportional to the change in magnetic flux, it says the rate of change. And whenever we have the word rate, we need to include divide by time. And so that's why we've got this divide by time. I also want to draw your attention to the fact that there's an N out there, and that N stands for the number of turns on the coil. And so very clearly, what we need to recognize is that the induced EMF is also directly proportional to the number of turns. And that summarizes for us those factors that are going to affect the strength and the magnitude of the induced current, the induced potential difference. But let's just see if we can make sense of one further thing. And I want to interpret it in terms of that negative sign over there. The man that did the interpretation for us was a man called Lenz. And so we talk about Lenz's law. And in a more detailed way, he says that the EMF induced in a coil opposes the change in magnetic flux. And it does that by exerting a force on the magnet that is moving towards the coil. It opposes that change in magnetic flux. Remember, without the change in magnetic flux, there'd be no induced EMF. And so it might sound a little bit complicated. Let's simplify it a little. And so what we recognize here is that if I have a coil, and I'm just going to use this red line, red pen to indicate the magnet, and I'm going to use a blue line to indicate the coil, and I'm going to connect it to a galvanometer. At the moment, it's reading 0. And I'm going to say to you, I'm going to use a force to push the magnet towards the north, towards this coil. And so what Lenz's law says is if you push a north pole towards the coil, it will try and repel that motion. It will try and exert a force to prevent there being a change of magnetic flux. Remember, when it's far away, the magnetic flux is low. As it comes closer, the magnetic flux is getting bigger because there are field lines passing through the middle of the coil. And we want that to be reduced. So it's going to repel it. And so as the the North Pole moves towards the coil, what happens to the pole at the end of the coil? Well, it's going to develop a North Pole because North repels North. So it wants to create repulsion. Okay? It repels the magnet. And in that process, by creating a North Pole, there is an induced EMF, there's an induced current that passes through the coil. Let's do one more situation, and let's make sure that we've got that very clear. So if I'm moving this North Pole towards here, this end is going to become a North Pole. Recognize that if the North Pole moves away from the coil, so if I go back to that previous diagram over there and I say, let me just erase the writing there, and I'm going to say I'm moving the North Pole away now. In which direction is the pole going to be at this end? Well, it's going to be a South Pole because it wants to pull it back. So whatever the pole coming towards it, it wants to repel. If there's one that's moving away, it wants to pull it back. And so we recognize over here that if there's a North Pole moving away from the coil, the coil develops a South Pole. It wants to attract the magnet. And so that really summarizes for us the principal points of electromagnetic induction. I hope you've got those main points together. Take a short break and we'll see you directly after that.